All right. When we start trigonometry, so trigonometry, Greek word for tree or tri meaning three, gon meaning angle, metry meaning measure. Okay, so talking about triangles here. All right. The entire course is predicated off of our knowledge about triangles. What we're going to find out in these first two chapters is like 5.1. What we do in 5.1 is going to be eerily similar to what we do in 6.1. What we do in 5.2 will be eerily similar to what we do in 6.2, and so forth throughout both chapters. Very similar type problems, but what happens in 5.1, 5.2, 5.3, we're going to look at this content through the perspective of triangles and knowing like 180 degrees of a triangle and all that kind of stuff. Okay. When we get into chapter 6, we look at all the same type of curriculum and content, but through the lens of what we call the unit circle. Has anybody heard the unit circle before? Maybe a little bit. Okay, so unit circle is a tool that is created from triangles, but its use is with a circle. Okay, we'll get there and talk about it eventually. I just want to make sure that you understand that these two chapters are really the same thing, just looking at them in a different perspective. And eventually, obviously, it'll be up to you which one you use, which perspective you use. But the course is going to be taught using, after we get through chapter 6, everything then will be based off of the unit circle. Okay. Every high school and college trig course is usually conducted that way. Okay. When we talk about trigonometry, we're going to obviously study triangles and groups of three angles and that sort of thing. But the number one thing to talk about is an individual angle. Okay. So an individual angle is going to have two sides. We call them rays. They're going to have a common endpoint. That common endpoint up there, that picture on the left, the common endpoint is O. And on the right, the common endpoint also is O. But you've got the two, that's called the vertex. Okay. One of our rays, which is going to be one of our sides of our angle, is going to be called the initial side or the initial ray. And the other one is called the terminal side or the terminal ray. Okay. Now, the way that we're going to construct our angles and we're going to view them is in the coordinate plane. Okay. Where basically what's going to happen is that we're going to have this ray right here. Okay. This is going to be called my initial ray. Okay, I'm going to use the blue one. So the blue one is called our initial ray. It is the positive x-axis, correct? Okay, or it aligns itself with the positive x-axis. Now, I can make that ray as long as I want. It's still the same ray. Does that make sense? Rays go on forever in one direction. So if I make it go to there, or I make it go to there, it's still the same ray. And the angle that is created from that is going to be the same as the angle that's created from that one. Does that make sense? Okay, so it doesn't matter the length right now. For that ray. Once we take that ray, so that's going to be our initial ray, we're going to take that ray and start rotating it. Okay, so I'm rotating it, and I'm rotating about or around the point A. Okay, and then this measurement okay, this green measurement, it's the measurement of rotation that red ray took to put it where it's at. Does that make sense? From being the initial ray to where it's at now. That is the measure of our angle. Okay? And like I said, does that measure of that angle change at all when the length of that ray changes? No. Okay? And likewise, now, because I'm moving here in 2 dimensions, I'm going to be hard to Got to move this point straight down here. I'll try my best. But if I was able to stay on the correct ray there, you would see that moving that one's length would not change that angle. Make it 90. I make it 90, you can see the change in its length does not change that 90. Okay? But that is what we refer to as the measure of an angle. Blue side is initial, red side is terminal. Okay? Now, the rotation that I did, what direction am I rotating when I go from here, this being the initial ray, to that? Okay, that is counterclockwise, and that is the kind of standard movement that we use when we're working in the coordinate plane with angles. Okay, so we move counterclockwise. Okay. Last class said, well, what about, will we ever talk about that angle right there? Okay, a lot of times maybe in a geometry class we call it a reflex angle because it's bigger than 180, right? Okay. In geometry, all we ever talked about was angles that are either equivalent to that one or smaller, right? Okay. And the reason we did that is because, well, if I want to talk about let's say a 203.2 degree angle, it's actually more convenient in geometry to talk about the 156.8. Does that make sense? Okay. What do those two add up to? 360. Okay. In trigonometry, if I talk about this 203.2 angle, which we will do a lot, okay, there's nothing wrong with that. There's nothing bizarre about that. That's perfectly fine angle measurement to talk about, okay? But there is a direct link between that angle and that angle as well. So what we find out is that what I know about the angle of 23 or 233.8 is the exact same thing that I know about the angle of 126.2. Okay, so they will go hand in hand with one another. Does that make sense? Okay, so there's nothing wrong with talking about angles that are bigger than 180. Okay, another type of angle that we've never talked about would be if I start, so let's say the blue ray is my initial ray. What direction am I rotating now? Clockwise. Rotating clockwise. And that's not necessarily the preferred direction or standard direction. There's nothing wrong with it. Okay. But this angle right now of 41.02, that would be that angle right there. That's the rotation that we went from the blue ray to the red ray. But in order to tell everybody that we went in that clockwise rotation, that clockwise direction, we now refer to that as a negative 41 degrees. Does that make sense? Okay. Negative in rotation. Like you think about like negative maybe on the number line as like take away, right? Remove. Okay. That's not happening here. It's just, we still got 41 degrees. It's just that the negative tells us the direction we move. Okay. Kind of like maybe when we put the number line out and we start at 0, moving to the right, we define those integers or real numbers with positives, right? And moving to the left, we define those real numbers with negatives. Here, if I'm moving counterclockwise, we define those angles with positives. And if I'm moving clockwise, we define those angles with negatives. Does that make sense? So the rotation, the direction of rotation, and the sign that gets attached to that is important, okay? So what am I saying about that? Well, let's do this real quick. Let's say that if I go cosine of negative 41.02 degrees and ask this thing to evaluate it, you see it gives me 0.75. Let's see what cosine of 318.98 is. Still 0.75, right? Does that make sense? Okay. So the knowledge that we have about that red angle should be consistent with the knowledge that we know about that green angle. Okay, and we'll get into all that kind of stuff and how we determine those angles soon. Questions on that so far? All right, let's talk about, so we talked about angle measurement, the amount of rotation about the vertex to go from one ray to the other. Let's do this real quick. So, long ago, a group of people called the Babylonians, you guys heard of them before, right? Okay. They are the people that we can accredit the 360 degrees to. Okay. They knew, so they were looking at this figure here. What's that figure right there called? Oh, not that one. Okay, so we got a hexagon here. And because these sides are all the same, and because the angles are all the same, what kind of hexagon is it? Starts with an R. Nope. Anybody remember the... Say it again? Regular. Good. Okay, so that's a regular hexagon. Okay. So what the Babylonians were interested in doing is coming up with the diagonals, or a series of diagonals, for this hexagon. They did that. And they gave 6 triangles. What do you know of those 6 triangles? They're all the same. Okay. What else do you know? They are isosceles. They are isosceles because what we call the radius of a polygon. So that distance right there is the same as that distance right there, correct? Okay. So the radius of our polygon is always the same. So they're all a bunch of isosceles triangles. But what we're able to even dig into a little bit deeper, and through just some measurement, we can find that if that distance is 3, oh, I didn't really get to I there, hold on. Intersect that. All right, so E, why isn't E showing up over there? I don't see E. I don't either. All right, so there to there, 3, there to there, 3, there to there, 3. So not only are they isosceles, they are equilateral. And if they're equilateral, they're also equiangular. And if they're equiangular, don't they all, I can move it, all those angles right there have to be 60 degrees if they're equiangular? Okay. So the Babylonians knew all that. So where does that get us to 360? Well, what's 60 times 6? 360. And that's nice. That's convenient. We were able to figure that out, and they knew that. How does this relate to circles? Anybody have any ideas? There is 360 degrees in a circle, but why? Why does a hexagon here have any relation to a circle? Kinda. If I do this, if I draw a circle with the same radius, take my circle, the same radius as the hexagon, does that circle pass through all 6 vertices of the hexagon? Okay, so that was something that they were intrigued by, interested by. And they said, well, if there's 360 degrees in that hexagon, but we wipe the hexagon away, should there still be 360 degrees in that circle? Yeah. That was their argument. Okay? And if you remember back to what we talked about in geometry, we called this angle right here a central angle. And then we said that this arc here was equivalent in regards to its measurement of that central angle. So this arc has it's a 60 degree arc. Okay? Now, there were other dimensions. We could talk about this as a length as well, which then incorporated a formula that we'll talk about here in the next couple of days. But that is where 360 comes from. Okay. And I think is that standard in any trig course? I don't think so. I never knew that in any trig course that I ever took in college or high school. Okay. Not until kind of investigating people, because I always get the question early on teaching, why is it 360? Well, that's why. Okay. Now, a degree then, by definition, is one 360th rotation all the way around that circle, right? Okay. If I were to tell you, I don't know if this is accurate, but let's say it's 150 miles to Cleveland, or 240 kilometers to Cleveland from here. Okay, now those are equivalent distances, 240 and 150. 150 miles or 240 kilometers. Which one are you more comfortable working with? The miles. Okay, because of our experience, right? Because you traveled 1 mile, you traveled 2 miles, you traveled 3. You understand? You can feel that. Okay, you travel 1 kilometer, 2 kilometers, 3 kilometers as well. But we've never identified or classified, defined that distance on a regular basis in America. Okay, so we are more comfortable with miles. Mathematically speaking, which one's better? Kilometers. Because it's based on units of 10, right? Okay. Think about miles. Miles are based on feet, 5,260 feet, right? Feet are based on inches, which are 12. And it just doesn't end up, because it's not consistent, it doesn't allow the mathematics to work real well. Okay? It bogs the math down working in U.S. customary. But if I'm using the metric system of kilometers, kilometers is 1,000 meters, that kind of thing, it's all based on powers of 10, that allows for calculations to be done easier. Okay? But again, we're not comfortable with the easier unit, right? Same thing happens in trigonometry. There are 2 units, degrees. You're comfortable with degrees, right? Been using those since whatever, okay, whatever grade. Okay, 5th grade, 6th grade, 7th grade. Using degrees all along. We could do some calculations with them, okay, but the way the rest of mathematics is designed, put together, calculus, complex number theory, linear algebra, a lot of your work beyond this class doesn't mesh well with degrees. Okay? It can be done, but it bogs the calculations down. Okay? The unit that we prefer to use in those classes and this class is what we call a radian. Okay? Anybody know what a radian is? Okay, so something new to us, right? So my analogy is that a radian is much like the kilometers were to us, right? Miles are like the degrees are like the miles, but radian is like kilometers. It's kind of foreign to us, but it's going to be what we prefer eventually. A radian by definition, and I still think this is, after reading this definition, you might still have no idea what it is, so I'll give you a demonstration here in a minute. But it's the length of the arc that is inside of an angle formed by 2 radii that are 1 unit long. Okay? Yeah, exactly. Okay, so I'm going to show you. Okay? And I posted this. I think I put it in Schoology so that you can come back to it. Yeah, under 5.1 in Schoology. We're going to try to embed it better than this link, but I found this on Twitter several years ago, and I think it's the best demonstration of what a radian is that I've ever seen. Okay, so what we're going to do is we're going to take out this. We're going to start at the origin. Okay, so faintly, can you guys see the gray axes here? Okay, and we're going to trace out this red segment, and we're going to rotate that red segment. And what do we create? A circle. So that was the most rudimentary, basic compass we could ever make, right? Just a straight line and rotate 1 end. Okay. What is that red segment called for that circle? Radius. Okay. Radius is the namesake for radians. That's where there's a link between the radius and radians. Does that make sense? Okay? And here's the link. We are going to take that radius and we are going to move it out of the circle, so it's right there. Still the same length, right? Is that okay with everybody? So I moved it, but we're not changing the length here. The next thing we're going to do is we're going to lay that thing along the circumference of the circle. We're just going to lay it down, form it to the circumference. So this is the idea of like that red distance is like a piece of yarn, okay, or a piece of string. I move it outside the circle, it's still the same piece of string, right? It's still the same length, correct? Now I take that string, and because it's malleable, I can move, I can change its contour, but it's still the same string, right? So it's still the same length. That's still R. Does that make sense, everybody? Okay. So in our definition, that right there, that red distance, in our definition here, is the length of the arc. It's that part right there. Okay. It says that is inside of an angle formed by two radii. Well, what two radii? Those two radii. Okay. So that is 1 radian right there. Does that make sense? Okay. Now, if I were to do this thing and break the circle up into 360 little slivers, each one of those would be an angle, right? Or a degree, correct? This, I can't get 360 of these inside that circle, correct? So this is not equivalent to a degree. 1 radian is approximately like 57 degrees. Okay, and we'll talk about that here in a moment. But if I do this, that's 1 radian. That would be a 2nd radian. And here's a 3rd radian. Okay. Now what happens is there's still a little tiny sliver there, a little tiny distance that gets me from this red point here to the negative x-axis, right? Okay. That little distance, if we were to calculate it, is 0.14129. It goes on forever, never repeats. And when I add it to 3, it gives me pi. Okay? So pi radians is equivalent to how many degrees in this situation? 180 degrees. There is your conversion. Okay? Remember talking about like 1 mile is equal to 1.61 kilometers? Okay, that's a conversion from miles to kilometers, right? Okay. Or maybe, I think maybe a more precise conversion is that 1 inch is 2.54 centimeters. Okay, but that's a conversion from one unit to the next, one system to the other system. Okay. Pi radians is equivalent to 180 degrees. Not pi over 3. Pi over 2. So pi over 2, cut 180 to get 90, right? Cut it in half. So to take pi and cut it in half, you get pi over 2, right? So pi over 2 is exactly the same thing as 90 degrees. Okay. If I continue this process all the way through, so that's pi radians, rotate all the way through, there we've rotated 2 pi radians. So 2 pi radians is exactly the same thing as how many degrees? 360. So the pi equals 180. That is just the simplified version of 2 pi radians equals 360 degrees. Does that make sense? Take 2 out of it. So that, what we're saying here, and this is going to be something we'll talk about in greater detail later on, but not only is, if this is R, okay, what is the circumference of this circle, if that is R? 2 pi R. There's the 2 pi. Okay, that's where the 2 pi in that formula comes from. Okay, and what we're going to find out is that R that we use here, we like it to be 1. So that if that is 1, like the definition said, then not only is this angle here equivalent to 2 pi radians, okay, so this angle here that's kind of all colored in right here would be equal to 2 pi radians. This length of this arc is also 2 pi radians. Does that kind of make sense? So there's a one-to-one kind of connection there with the angle and the length, if we're talking about a radius of 1. And when we talk about the radius being 1, what is the number 1 referred to in mathematics? It starts with a U. Unit. Okay? I said chapter 6. You anybody remember what I called chapter 6? What I was going to talk about? The unit circle. So the unit circle is just it's this circle here, but the radius is going to be 1. Okay? And what that unit circle tells us then is everything else we ever need to know about any other circle in any triangle that we ever come across. Okay? So like Jim said, does that mean that 90 degrees is equal to pi over 2? It absolutely does. And it means that 30 degrees is pi over 6. And it means 60 degrees is pi over 3. It means pi over 4 degrees is 45 degrees. Sorry, pi over 4 radians is 45 degrees. And those are things that I can rattle off the top of my head because I've been doing this for 20 years. You guys will be able to do those conversions eventually. Okay, and that's what we're going to try to work on a little bit tomorrow, is how we do those conversions. But if you can convert miles to feet, if you can convert kilometers to miles, inches to kilometers, that kind of stuff, you can do unit analysis from maybe a science class, or you guys had me in geometry, we did a unit in geometry over it. You should be able to have no issues with converting radians to degrees or degrees to radians. Okay? What you're going to find out is that you're going to be more comfortable with degrees throughout the entire course. But it boils down to math. Okay? You might be more comfortable with degrees, you might understand things a little bit better with degrees, but radians make the work easier. Okay? I will introduce a lot of the concepts, even though radians make the work easier, I will introduce a lot of concepts with degrees first. So I think we can understand those better, we can visualize things better with degrees. Does that make sense? But then we'll work into the same kind of thing with radians, try to express and visualize things with radians. No homework tonight. Just a reminder that you do not need anything new for this course. The one thing that I would do, GeoGebra is going to be useful in this course. Okay, so maybe you want to download that. I would use, if I'm going to download it, version 5.0, I think is what's called on their website. There's a version 6, but it's like they try to make it fancy, and the user interface is not very nice. Your TI-83s, 84s, they'll be beneficial at some point. Desmos, not as useful as it was in college algebra. So we use a lot more GeoGebra in this course.